In this section, we talk about various ways to modify Turing machines. Some of them try to restrict the power of ordinary Turing machines. Others try to expand the power of Turing machines. We will talk whether they succeed or not by showing these modified Turing machines can be simulated with the machines we know about. But first, let's review the components and working mechanism of ordinary Turing machines. It has an infinite one-track tape, which is bounded on the left end and unlimited on the right end. Each cell contains exactly one tape symbol from the finite tape alphabet, gamma. It has a finite set of states to store some information and a read-write tape head that can move left and right on the tape. When the machine is in a certain state Q and the head is over a tape cell containing a symbol A, and if the transition says delta QA equals RBL, the machine writes the symbol B replacing the A on the tape and goes to state R. After that, the head moves to left. Initially, M receives its input W on the leftmost n cells of the tape if W has n symbols, and the rest of the tape is filled with blank symbols. The head starts on the leftmost cell of the tape, and the machine runs according to the delta, the transition function. For convenience, we use a configuration to describe the situation of the machine. A configuration UQV means the tape content is UV followed by infinite many blank symbols. The machine is at state Q, and the tape head points to the first symbol of V. Since we want to check whether some modifications limit or expand the power of ordinary Turing machines, we need to show whether they are equivalent to some less powerful or more powerful machines. To do so, we show two machines are equivalent by showing that one machine, M1, can simulate the other machine, M2. We set up the start configuration of M2 according to the start configuration of M1, and for each transition in M1, define the corresponding transitions in M2 that achieve the same result. For one single transition in M1, it is okay to have multiple transitions in M2 to achieve the same results. Among various ways to restrict Turing machines, some of them actually limit the power of Turing machines. Others have no effects. And among all the attempts to expand the power of Turing machines, they share the feature of unrestricted access to unlimited memory, and they are equivalent in power with the ordinary Turing machine, so long as they satisfy some reasonable requirements. For example, the ability to perform only a finite amount of work in a single step. Intuitively, a machine that can do infinite amount of work in a single step is more powerful. Now let's take a closer look at the ways to modify Turing machines. Changes can be done on the components of a Turing machine. Using multiple tapes, or a two-way infinite tape, or a multi-dimensional tape are attempts to extend Turing machines by adding power to the tape part. Using multiple heads on a single tape tries to add power to the tape head part. Adding a stay put option to the head changes the transition function. On the other hand, restricting the head positions to only the portion of the tape covered by the input limits the power of Turing machines. Its equivalent machine is a linear-bounded automaton that recognizes context-sensitive languages. We will not talk about the details of this machine. Replacing the move left option with the stay put option also limits the power of the Turing machine. It is actually a homework question. We will talk more about it in a little bit later. Restricting the machine by not letting it write blank symbols actually does not affect the power of Turing machines. Because we can use a different symbol to mean a dirty blank symbol, instead of writing the original blank symbol that can be found but not written, we can write the dirty blank symbol to achieve the same results. Now for the homework question, a Turing machine M with stay put instead of left cannot recognize the same class of languages as ordinary Turing machines. What class of languages can this kind of machines recognize then? In class, we only talked about 2 classes of languages that are below Turing recognizable languages in hierarchy. So a big hint for you. Do you think they recognize regular languages or context-free languages? If you think they recognize regular languages, then you try to simulate M with an NFA D. If you think they recognize context-free languages, then you try to simulate M with the push-down automaton D. After you think carefully and make the choice, you need to show the details how you simulate M with D. You specify different components of D. Here are some aspects to help you construct D given machine M. So the alphabet of D is gamma. For any symbols used by M, you probably also want to use it in D. How about states? Do you need more states? And how do you track the head position? There are Q times gamma many transitions in M. Do you want to use states in D to memorize each one of these combinations? For each transition, delta QA equals RB and ROS. How do you define the transitions of D to accomplish the same results? Remember here A means the head points to a cell containing A, so it is the head position. Once you have simulated M with D by giving all those details, you need to do the other direction. Show that M can simulate D, because you don't want D to be more powerful than M. If in this step you find that there are some things that D can achieve but M cannot, then probably you made a wrong decision by choosing D to be an NFA or a PDA. In this direction, you do similar things. Given the components of D, how do we construct M? Specify the states of M and the transition function of M accordingly. Alright, enough hints for this homework problem. There are more hints for another problem later. Now let's move on to an example that tries to extend ordinary machines. A Turing machine with doubly infinite tape. Its tape is infinite to both the left end and the right end. The tape is initially filled with blank symbols except for the portion that contains the input. In an ordinary Turing machine, there is a left end, and whenever the machine tries to move left once it hits the left end, the move stays in place. Now in this modified machine, this restriction is lifted. The head never encounters an end to the tape as it moves leftward. But we can show that removing this restriction does not add power. We show that these two machines can simulate each other. To simulate an ordinary Turing machine M2 with a doubly infinite tape Turing machine M1, it only needs to mark the left-hand end of the input so that it can prevent the head from moving off of that end. For example, it can put a special dollar symbol on that cell and move all input content to the right by one cell. Whenever the machine reads a dollar symbol, it moves right and continues the computation there. For the other direction, to simulate the doubly infinite tape Turing machine M1 by an ordinary Turing machine M2, we show how to simulate it with a two-tape Turing machine M3, which was already shown to be equivalent in power to an ordinary Turing machine in class. The first tape of the two-tape Turing machine M3 is written with the input string, and the second tape is filled with blank symbols. We cut the tape of the doubly infinite tape Turing machine M1 into two parts, at the starting cell of the input string. The portion with the input string and all the blank spaces to its right appears on the first tape of the two-tape Turing machine, and the portion to the left of the input string appears on the second tape, in reverse order. Computation done on M1 at cells right to starting cell of the input string is simulated in tape 1 of M3, exactly as it is done on M1. Computation done on M1 at cells left to starting cell of the input string is simulated in tape 2 of M3, with L and R reversed. For example, if in M1 the transition function says move left, then on tape 2 of M3 it should move right. This is one way to simulate the doubly infinite tape Turing machine. Now I want to show you another way. We simulate the doubly infinite tape Turing machine by a single tape Turing machine with multiple tracks. It is a common trick to use a single tape with multiple tracks to simulate other machines. I believe you can use it in your homework answer somehow. In this example, we will use a two-track tape. Now the tape alphabet is not gamma, but gamma times gamma. Visually, you can see now a single tape symbol in the new machine has two ordinary symbols, one on the top track, one on the bottom track. The cell circled in red is a single tape cell in the new machine. If the doubly infinite tape Turing machine works as cells right to starting cell of the input string, the new machine works accordingly on the top track. Whenever the doubly infinite tape Turing machine moves to the left of the input region, the new machine works on the bottom track with L and R reversed like before. If in M1 the transition function says move left, then on the bottom track of this new machine it should move right. The working mechanism of this new machine is similar to the two-tape machine before because the main idea is the same. We fold the tape somehow. Okay, let's use another example to familiarize with this multi-track idea. A Turing machine with a multiple, say k heads on a single tape, has transition function delta q a1 through ak equals r b1 through bk and d1 through dk, where di means the moving direction of that head I. The meaning of this transition is that the machine is at a current state q, and the head 1 is reading the symbol a1, head 2 is reading the symbol a2, and likely head k is reading the symbol ak. According to the transition, the machine will move to state r, Head 1 replaces A1 with the symbol B1 and moves to the direction D1. Head 2 replaces A2 with the symbol B2 and moves to the direction D2. And likely, head K replaces AK with the symbol BK and moves to the direction DK. In summary, there is a single tape but K heads that can read and write at different places on the tape in a single move. Now we show that this machine can be simulated with a single tape Turing machine using multiple tracks. We want to keep track of all the K heads, so we use K+1 tracks. The first track holds the input string and is the place all the computation is done. The other K tracks keep track of the K heads. In each of these K tracks, a special symbol X is used to mark the head position. This machine has the same set of states as the original machine. The computation is done similarly to the original K-head Turing machine. Use the previous transition as an example. Say delta Q A1 through AK equals R, B1 through BK, and D1 through DK. The K-track machine will move from state Q to state R. The second track has an X below the symbol A1 in the first track that marks the head position of head 1. So it will replace this A1 with the symbol B1 and moves this X to the direction D1. When I say move X to D1, the meaning of that is replace this X with a blank symbol and replace the adjacent blank symbol with X according to the direction D1. All the other tracks function in the same way. AK is marked by an X in the last track, and it will be replaced with BK. After that, the X is moved to direction DK. One thing that needs to take care of is that if multiple heads point to the same cell, what should the machine do? In this case, a reasonable policy is, for example, to give priority to the highest numbered head. In other words, write BJ on the tape if and only if j is greater than I. I hope after this example you have a good understanding of the mechanism of a multi-track tape Turing machine. You can use those tracks to keep track of head positions, or use them to do computation on input string, or store some other information. If you like, you can use this idea creatively in your homework answer. Let's check that problem in homework 10. It's a two-dimensional Turing machine with the usual finite state control, but the tape is a two-dimensional grid of cells, infinite in all directions. The input is placed on one row of the grid, with the head at the left end of the input control in the start state, as usual. The head can move one position on the grid to adjacent cells. Acceptance is by entering a final state as usual. We want you to show that the languages recognized by these two-dimensional Turing machines are the same as those recognized by ordinary Turing machines. In other words, we want you to show that this kind of machines can be simulated with an ordinary Turing machine or a Turing machine that is equivalent to an ordinary Turing machine, like multi-tape machines, non-deterministic machines, and so on. You can choose your favorite machine to do the simulation so long as you can succeed. One possible way is to simulate the two-dimensional machine with a multi-track single-tape machine. Here we need to define an indexing for the cells in the two-dimension space. By assigning an arbitrary origin, say the cell of the first symbol in the input string, and positive and negative directions, we can say that each cell has index I1, I2, where I1 and I2 are natural numbers. But representing this on a single tape is not as simple as you may think. These indices are not bounded. so we cannot store them in a single cell using a decimal number. In other words, this solution is wrong. The reason it is wrong is that the tape alphabet should be a finite set, so it is not possible to store infinite many natural numbers. Now you can think of how you can address this problem. Is it possible to use unary numbers instead of decimal numbers? Although to store the same numeric number, a unary number takes more cells than a decimal number. But space is not a problem because the tape is infinite on the right end. Also, using unary numbers for indexing keeps the tape alphabet finite, because we only added one symbol to the existing alphabet. You might think of using a lot of tracks to store each digit in the unary number, like you store the unary number vertically. But remember that the number of tracks needs to be decided and cannot be changed afterward. So you probably cannot store an arbitrarily large unary number with a finite number of tracks. Alright, enough hints for this problem. Of course, you can use other machines to do the simulation. It's your choice. That's all for today. Leave a comment if you have any questions.